Pluto is a distant and elusive planet, once regarded as a member of our planetary system, though its status has since been reclassified as a dwarf planet. Despite this, it remains an object of significant interest. Recently, however, renowned astrophysicists Neil deGrasse Tyson and Michio Kaku have reignited discussions surrounding Pluto with their startling claims. They have suggested that Pluto might be on a collision course with Neptune in the distant future. This revelation has raised questions. How could such an event occur, and what would the implications of such a catastrophic event be? Are we witnessing an intriguing cosmic anomaly, or is there a deeper reality behind this potential disaster? Join us as we explore the potential effects of a Pluto-Neptune collision. Pluto, formerly classified as the ninth planet, has sparked considerable interest even after its reclassification to a dwarf planet. Its role in the universe continues to captivate scientists and stargazers alike. A primary reason for the renewed interest in Pluto lies in its orbital path, which dangerously intersects with Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku have both warned of a potential crash between the two bodies, a collision that could have dire consequences for the Earth. But how exactly could this happen? Unlike the other planets in our solar system, Pluto's orbit is unlike any other. It takes an extraordinary 248 years to complete a single orbit around the Sun. Since its discovery in 1930, Pluto has yet to finish even one full revolution. But what makes Pluto's orbit even more intriguing is its eccentric and elongated shape. Unlike the nearly circular orbits of the main planets, Pluto's path is far more erratic. Furthermore, Pluto's orbit is tilted at a significant 17 degrees relative to the ecliptic plane, making its movement even more unusual. This tilt adds a layer of complexity to its already erratic orbital behavior, and it is this complexity that has made Pluto's path so fascinating to astronomers. One of the most remarkable aspects of Pluto's orbit is the intersection it shares with Neptune's. For a brief period of about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune. This orbital overlap raises the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. Following Pluto's discovery, astronomers became intrigued by its unusual orbit and sought to understand its path through the solar system. Unlike other planets whose orbits are relatively stable and close to the ecliptic plane, Pluto's orbit stands out due to its steep inclination and irregular shape. The mystery deepened as astronomers realized that Pluto's path crosses that of Neptune. This led to the investigation of Pluto's orbit, which revealed its peculiar stability despite these intersecting paths. This phenomenon can be understood through the lens of the three-body problem in celestial mechanics, which involves the challenge of calculating how three objects in space, like Pluto, Neptune, and the Sun, interact gravitationally. The three-body problem, in essence, seeks to predict the movements of three celestial bodies, factoring in their gravitational pulls and initial positions. In Pluto's case, the solution to the problem lies in understanding how its orbit, Neptune's orbit, and the Sun's gravity work together. Terms such as asynchronous libration, orbital precession, and Vixel oscillation help explain the stability of these orbits. For instance, asynchronous libration refers to the specific relationship between Pluto and Neptune. Whenever Pluto crosses Neptune's orbit, it is always at least 90 degrees away from Neptune in space. This ensures their orbits don't overlap. Orbital precession, on the other hand, refers to the upward movement of an orbiting body. For Pluto, this means that when it comes closest to Neptune or any other large planet, it is positioned far above their orbital plane, creating an additional protective buffer against potential collisions. Another crucial factor in this equation is Vixel oscillation, which describes how objects like Pluto, Neptune, and the Sun influence each other's motion through their gravitational pull. This interaction plays a role in maintaining the stability of Pluto's orbit. Despite Pluto's seemingly erratic orbit, the Vixel oscillation helps maintain order, ensuring Pluto's motion remains relatively stable over long periods. Though space may appear unpredictable, these gravitational forces work together to keep Pluto's orbit intact and prevent it from straying off course or colliding with Neptune. The three-body problem is pivotal in understanding the behavior of celestial bodies and their movements. Mathematical simulations in the 1980s revealed that, despite the stabilizing factors of Pluto's orbit, minor changes in its initial conditions could lead to significant long-term deviations. These findings have been crucial in understanding the intricate nature of Pluto's path. Even though Pluto's orbit is unpredictable, its stability over thousands of years is noteworthy. Scientists have used advanced modeling to better grasp how planetary giants like Neptune, Jupiter, and Saturn influence Pluto's movement through space. Neptune, for instance, has a unique relationship with Pluto in which Pluto completes 2 orbits around the Sun for every 3 orbits Neptune completes. This resonance plays a key role in maintaining the stability of Pluto's orbit. But Neptune is not the only planet playing a role. Jupiter's immense gravitational influence also helps keep Pluto's path on track. Studies have shown that Jupiter's gravity is strong enough to provide a stabilizing effect on Pluto, ensuring that its orbit remains steady over millions of years. The gravitational forces exerted by Neptune, Jupiter, and Saturn work in tandem to ensure Pluto's orbit remains stable. These complex forces are fundamental to the overall stability of the solar system. Without these stabilizing factors, the solar system would be a far more chaotic and unpredictable place. Bodies like Pluto could easily be ejected from their orbits, or worse, collide with other celestial bodies, triggering a chain reaction of events. Pluto's case serves as a reminder of the dynamic nature of the solar system. Though a future collision with Neptune seems unlikely today, ongoing research and the study of its orbit are critical in understanding how our solar system works. The study of Pluto's orbit highlights the complexities of orbital mechanics and gravitational interactions between planets. Despite the seemingly chaotic nature of space, these gravitational forces ensure that celestial bodies like Pluto continue their paths in relative stability. The possibility of a collision between Pluto and Neptune is a reminder of the ever-changing nature of space and the importance of continued observation. As astrophysicists like Neil deGrasse Tyson point out, our understanding of space is always evolving. Tyson, who played a major role in Pluto's reclassification as a dwarf planet, encourages a shift in perspective, seeing this change not as a loss but as a reflection of the expanding knowledge about our solar system. Tyson emphasizes the importance of curiosity and exploration in unraveling the mysteries of the cosmos. While the future of Pluto's orbit remains uncertain, the possibility of a collision remains a topic of interest. Studies of Pluto's orbit, aided by mathematical models and simulations, continue to offer new insights into the dynamic behavior of planets and other celestial bodies. Understanding how these forces interact helps astronomers predict future events and offer a clearer picture of the future of our solar system. In conclusion, Pluto's orbit and its resonance with Neptune represent an incredible example of the complex interplay of gravitational forces in the solar system. While the likelihood of a collision between Pluto and Neptune is minimal, the investigation into these forces continues to reveal surprising insights. The ongoing research into Pluto's orbit not only contributes to our understanding of space but also serves as a reminder of the intricate and ever-changing nature of the universe. As we continue to study these distant worlds, we gain a deeper appreciation for the vastness and complexity of the cosmos. As we continue to probe the mysteries of Pluto's orbit, it becomes increasingly clear that this distant world provides a valuable case study in celestial mechanics. While Pluto's orbit seems chaotic and unpredictable on the surface, the interplay of gravitational forces and orbital dynamics ensures that it remains relatively stable over long periods. This stability is critical not only for understanding Pluto itself, but also for expanding our broader understanding of the solar system and the forces that govern the motion of celestial bodies. The role of gravitational resonance, particularly between Pluto and Neptune, is key in explaining the apparent stability of their orbits. This resonance, where Pluto completes 2 orbits around the Sun for every 3 that Neptune makes, essentially locks their paths in such a way that the 2 planets will never collide. This dynamic relationship showcases the remarkable precision of the forces at work in the solar system. The gravitational pull between these 2 bodies, combined with the influence of other planets like Jupiter and Saturn, ensures that their orbits remain synchronized and stable. Yet, as scientists like Neil deGrasse Tyson continue to emphasize, our understanding of these complex gravitational interactions is always evolving. While current models predict a stable future for Pluto's orbit, there are still many uncertainties. Small changes in the initial conditions, such as the position or speed of Pluto, can lead to unpredictable changes in its long-term orbit. This is why ongoing research and continuous monitoring of Pluto and its surroundings are vital. As we develop more advanced simulations and refine our understanding of celestial dynamics, we are constantly learning new things about the nature of space and the forces at play. Another important factor to consider is the broader context of the solar system's evolution. Over the course of billions of years, the gravitational interactions between planets and other celestial bodies have shaped the orbits of objects like Pluto. These interactions are not static, As the solar system continues to evolve, the positions and movements of planets, moons, and other bodies can shift, which could have an impact on the stability of Pluto's orbit in the future. In particular, the long-term changes in the Sun's behavior will undoubtedly affect the entire solar system. As the Sun ages, it will undergo significant transformations, eventually expanding into a red giant. This expansion, which is expected to occur in about 5 billion years, will likely lead to dramatic shifts in the orbits of the inner planets. While this will have a more immediate impact on Mercury, Venus, and Earth, the outer planets, including Neptune and Pluto, may also experience significant gravitational forces that could alter their positions in the solar system. It is in this distant future that the potential for a shift in Pluto's orbit could increase. If the Sun's expansion leads to changes in the gravitational dynamics of the solar system, the resonances that currently stabilize Pluto's orbit might be disrupted. While this remains a distant possibility, it underscores the complex and ever-changing nature of the universe. The dynamics of the solar system are in constant flux, and our understanding of these changes is limited by the long timescales involved. Further complicating the situation is the presence of the Kuiper Belt, a region beyond Neptune that is home to many small icy objects, including Pluto. The Kuiper Belt remains an area of great interest to astronomers, as it harbors many objects with highly eccentric orbits. Some of these orbits even intersect with Neptune's, suggesting that the gravitational influences of these bodies could potentially affect Pluto's orbit as well. As we learn more about the Kuiper Belt and the interactions between its objects, we may gain additional insights into how Pluto's orbit could evolve. The study of Pluto's interactions with Neptune, as well as the broader dynamics of the solar system, is not just of academic interest. These investigations have broader implications for our understanding of celestial mechanics, the stability of planetary systems, and the evolution of solar systems in general. By examining the forces that keep Pluto on its current orbital path, scientists can gain valuable insights into the behavior of other distant worlds and the mechanisms that govern their motion. These findings could have implications for the study of exoplanets and the search for habitable worlds beyond our solar system. Astrophysicists and space scientists continue to refine their models and simulations, using increasingly sophisticated tools to predict the behavior of Pluto and other objects in the solar system. These simulations rely on complex mathematical equations that account for the gravitational influences of all the bodies in the solar system, and they have been instrumental in improving our understanding of the long-term behavior of Pluto's orbit. While these models are not perfect, they provide a clearer picture of how the planets and other celestial bodies interact, and they offer valuable predictions about the future. As new data from space missions and observatories continue to pour in, the accuracy of these models will only improve. Observations of Pluto, as well as other distant objects, will help refine our understanding of how these bodies move and interact with each other. In the future, we may be able to make even more precise predictions about Pluto's orbit and its relationship with Neptune and other planets in the solar system.